So we are discussing the real numbers, and we have seen two very important theorems, you can say, or properties you must learn, understand. Now let us revisit the rational numbers and decimal expansions. We have seen in class 9 that a rational number can either be terminating decimal expansion or it can be non-terminating repeating decimal expansion. We also call it as recurring. What we are going to see now is this P by Q. What is the possibility by just viewing it and just by a little effort you can find out whether it is terminating or non-terminating, repeating or recurring. Let us consider certain example. This 0.375 can be written as 375 by 1000, and this 1000 can be written as 10 cube. Similarly, this one 23348 by 10 to the power 4. And why we have written this 10 to the power 4 is very important. This 10 can be written as what? 10 is 2 into 5. So now 10 can be written as like this, 2 cube 5 cube, and this can also be written like this. Similarly, this one. Can you find out any pattern? You see that these numbers, they have in the denominator either 2 or 5 or both, either 5 or 2 or both. So we have a denominator, as you can see, 2 and 5 here, and now we can expect that these numbers are actually terminating. They are terminating decimal expansion of what number? Let us backtrack it. Because 10, if it is a prime factor, 2 and 5 are primes. So you can see that the form is either 2 to the power say some n and 5 to the power say some m. So if in the denominator you have 2 to the power n and 5 to the power m, you can very well say from this discussion that these numbers will be, or this decimal expansion would be terminating. Let us express it formally. If x is any rational number whose decimal expansion would terminate, and x can be represented in the P by Q form as we represented earlier, and P and Q are co-prime, and this Q can be factorized in the form 2 to the power n and 5 to the power m. M and n are non-negative integers. Then what we say here, we have just we have not given the decimal expansion termination. We have seen the decimal actually stops, means there is no recurring here. But a very important thing has come up, that if Q is of the form this, the number is stopping. Let us go backwards. 0.375, let us make it P by Q form. 3 by 8 can be written as 3 by 2Q, and we can multiply, because we have to make this 10, so we multiply it by 5 cube, and the numerator also 5 cube. So this is 10 cube. And we have found that it is of power 10 to the power 3. So this is 2 to the power n and 5 to the power m. So 2 to the power n, 5 to the power m, this number is going to be a terminating decimal expansion. Now take one more example. If this is your number, you want, okay, tell me what will be 1 by 7. So let us divide 7, 1, here is 1, take 0 and point. 7 1s are 7, 3, again take 0, 28, this goes on, again we get 30, and this from 1 to 7 is going to repeat. That means you will get 1 4 2 8 5 7 1 again, then 7 again. So this will be repeating, and you can say non-terminating or recurring. How did you get here? C 1 by 7. The denominator is not of the form 2 to the power m, 5 to the power m. The denominator is not of this form. Now by 1.5 and 1.6 we can conclude that if x is of the form p by q, if it is a rational number, and the prime factorization of q is not in this form 2 to the power n, 5 to the power m, where n and m are non-negative integers, then x has a decimal expansion which is non-terminating, which is not going to terminate, and it is repeating, so it is recurring. Right? Hope you understand. So let us summarize in this chapter what we have done. We have seen the Euclid division lemma. If we have positive integers a and b, then q and r are the whole numbers which will exist, so that there is a is equal to bq plus r form. R lies between b and 0. Also we have seen the algorithm, how to find out the HCF of two numbers a and b easily. We take q and r of this form, a and b, and r lies between 0 and b. If r becomes 0, we conclude that b is actually the HCF. Otherwise we repeat this procedure till r becomes 0, and we finally declare that b is the HCF. The fundamental theorem of arithmetic says that every composite number can be expressed or factorized as product of primes, and this factorization is going to be unique. If p is prime, p divides a square, p will divide a also. This is a, where a is a positive integer. We have proved root 2 and root 3 to be irrationals by a method of contradiction. About termination and non-termination or recurring, this p by q, if q can be represented in the form of 2 to the power n, 5 to the power m, we say that this decimal expansion is going to terminate. If q is not in the form of 2 to the power n, 5 to the power m, then this x is non-terminating, repeating, or recurring. One thing you need to remember also, that p into q into r was not equal to HCF PQR into LCM PQR. This didn't hold. But we do have a property, or we do have a relation that you can use in your questions. LCM of PQR can be taken as multiply PQR, take HCF of PQR, and then take pairwise, means PQ, QR, and PR. Similarly, for HCF PQR, take multiplication of PQR, take LCM of PQR. Now pairwise LCM, PQ, QR, PR. So this was all about the real numbers, and we'll be taking the next chapter shortly. Till then, thank you so much. Take care of yourself.